Hey there, AP Chem scholars. Today we're going to into Unit 4, Section 2, which is about net ionic equations. Now, there's a lot of assumptions that go into calling it net ionic equations, so this is really going to be a little bit longer than the last section, that's for sure. So when we talk about net ionic equations, we have to be talking about aqueous reactions. And if we're talking about aqueous reactions, then the best place to start is to talk about solubility rules of things dissolving in water. So again, something you should be somewhat familiar with. Let me slide me over out of the way. Okay, the solubility rules we've talked about before. You should be somewhat familiar with them. Okay, we're talking about ionic compounds, or specifically salts. Okay, which compose anions, cations, and if they're soluble, that means they dissolve in water. So we expect that anything made with an alkali metal or an ammonium ion, regardless of what the anion is, to be a soluble salt. Conversely, if the anion is nitrate, acetate, chlorate, or perchlorate, we expect that to always form a soluble salt regardless of what the cation is. Okay, so those are the only two absolutes. The next two rules are sometimes rules. Okay, chlorides, bromides, and iodides are soluble except mixed when they're paired up with silver, lead 2, or mercury 1. Now, I don't think you're ever going to see an issue where you have to worry about the difference between mercury 1 and mercury 2, lead 2, or lead 4. Okay, so I usually just say look for lead, silver, mercury. Okay, I've never seen that issue, and I'm not going to try and trip you up with that either. Okay, so if it's lead 2 chloride, silver bromide, mercury 1 iodide, or some other combination, those are going to be insoluble, which means they will not dissolve in water. And ionic compounds are typically solids at room temperature, so if they're not in water, then we expect them to be solid. With sulfates, we see some of the same. Okay, we have exceptions of, my words don't match up with my pictures. Okay, so the exceptions are silver, mercury 1, lead 2, barium, calcium, and strontium. Now, calcium, strontium, and barium, we're talking about the bottom of the alkaline earth metals, and these three, again, are exceptions. So again, you can see that these three cations, lead, silver, mercury, don't form soluble salts very easily. Anything else we are going to assume, at least for now, is insoluble. Now, technically, there's a lot more solubility rules in this. Okay, these are the 5 that you need to be familiar with. So if I said something like, is copper 1 sulfate soluble, you have to know yes, it is. If I said that magnesium carbonate, is it soluble, you have to know it is not. All right, so that's key. You got to know these, and it's not something that's given on the AP. All right, so when we talk about the idea of solubility, just keep in mind that right now we're not quantifying it specifically. We're just talking about it in terms of whether something does or doesn't. Ionic compounds are all soluble to some extent, okay? But we tend to call them soluble, insoluble. For example, sodium chloride, I'm saying, is very soluble, where lead chloride is not soluble. Well, technically, lead chloride dissolves a little bit. Barely enough, not enough to really notice on a significant level, depending on the type of testing that you're doing, okay? But technically, yes, it does dissolve a little bit because the waters can gang up and pull. The problem is that when you're talking about these things that are insoluble, their bonds are actually much stronger. And so it takes a lot more water molecules just to pop off one ion. And so you end up with not a lot dissolving because so much of the water is basically being used to grab just a few ions. When we talk about these compounds, we usually talk about electrolytes, okay? Like you talk about with Gatorade, okay? Well, electrolytes are compounds that dissolve in water to conduct electricity, okay? And the reason why they do that is because of the abundance of ions. So something that is a strong electrolyte is going to have a lot of ions there because it dissolves and dissociates very well, okay? Whereas if it's something like I mentioned, the lead chloride, something that dissolves a little bit, okay, well, then you're only going to have a few ions, so it really doesn't conduct that well. But when we use the term non-electrolyte, that means it's not an ionic compound at all, okay? So sugar or sucrose would be a non-electrolyte. Yes, it dissolves in water, but it will not conduct electricity because there are no ions present, so there's nothing to help conduct electricity. So to be an electrolyte, it's got to be an ionic compound, and to be a non-electrolyte, it's going to be a covalent compound. I used the word dissociation a moment ago. Okay, dissociation has to do with how the water is separating the ions apart. The fact that the negative end of water are grabbing the cations and the positive ends of water are grabbing the anions and pulling them apart. So if we talked about hydrocyanic acid or HCN, when it goes into water, it is going to be separated into a hydrogen ion and a cyanide ion. Okay, remember this is dissociation. They have to have charges. We're talking about ions. It's hugely important that you always keep the charges on these particles when we're talking about it. Okay? So likewise, if it was mercuric chloride, which is what we would call mercury 2 chloride, we would get 1 mercury and 2 chloride ions. So you have to know your ions in order to understand what's going to happen. Okay? Now, again, technically, even a weak electrolyte does dissociate a little bit. So we could talk about it like something like HCN, for example, is a weak electrolyte. We can go into the idea of its dissociation, even though it's not really soluble. But of course, that's what defines the strength of an electrolyte. How well it dissolves and dissociates. Okay, has to do both to be considered a strong electrolyte. Please, again, keep in mind, dissociation is not decomposition. A lot of people look at things like this and tell me that they're going to, when it dissociates, I'm going to get 2 aluminum ions, 3 sulfur ions, and 12 oxygens. No, you're thinking of decomposition a little too much. Okay, decomposition is where it just breaks up into 2 or more pieces. We're talking about ions. So aluminum sulfate has to break up into aluminum and sulfate ions. Calcium carbonate has to break up into calcium and carbonate ions. Ammonium phosphate has to break up to ammonium ions and phosphate ions. The name says it all. So again, knowing the nomenclature makes this so much easier because then it means you know that you're getting ammonium ions, phosphate ions, or calcium ions, carbonate ions, etc. We already said aqueous reactions means that it's taking place in water. All right. So please understand that anytime we're talking about an aqueous reaction, we're going to eventually want to do net ionic equations. So it's never going to be a case at this level of me saying write out the net ionic equation. If I say write out the equation for a reaction and you know it's aqueous, it's got to be net ionic equation. Anyway, we already mentioned solubility rules and how well different things dissolve or don't dissolve. Okay, when we mix solutions, we tend to get these solids forming, these products that are not soluble, and we call those precipitates. Okay, so a precipitation reaction just means that we're mixing solutions of salts. Okay, now technically we could call it a precipitation reaction even if there is no reaction. And I know that seems a little weird because there should be a precipitate if it's a precipitation reaction. Precipitation reactions are really double replacement. We haven't gotten into that this year already, but you kind of know that idea already. So we're talking about taking 2 ionic compounds, swapping around the ions to make 2 new ionic compounds. So for example, if I take silver nitrate and ammonium phosphate, I get silver phosphate and ammonium nitrate. Again, look at the reactants versus the product. All I did is swap out the cations, or you could say I swapped out the anions, whichever way you want to look at it. Notice that I did not write in the phases. At this level, you do not have to write out the phases. However, you are expected to know. So looking at that you need to know which one of these substances would be your precipitate. You have to know that nitrates are soluble, ammonium compounds are soluble. So this is my precipitate. So if you want to write in the phases for your own benefit, you can. Okay, but we don't generally write them out at this level. You're just expected to understand this stuff and look. But they won't mark you down, and I won't mark you down if you do write out the phases, as long as you write them correctly. So the phases would be, this would be aqueous, this would be aqueous, this would be solid, this would be aqueous. Okay. When we write them out as full compounds, we call it the complete molecular equation. Now, from the complete molecular, we want to go to the complete ionic, and then the ultimate goal, of course, we said is net ionic equations. So, to talk about the complete ionic, that's where we now have to recognize dissociation. The second I put silver nitrate in water, it's not silver nitrate anymore. It's silver and nitrate ions. And since there was a 3 here, I'm going to carry that coefficient through, so I have 3 silver ions, 3 nitrate ions. When I put ammonium phosphate in water, it's not ammonium phosphate anymore. It's 3 ammonium ions and a phosphate ion. Again, the 3 here because there are 3 ammonium ions, but there's only 1 phosphate ion. Now this was our precipitate, so that means it doesn't dissolve, which means it can't dissociate. And then we had the ammonium nitrate, and that does dissociate, that is soluble, so we have 3 ammoniums, 3 nitrates. So this red equation here as shown with all the ions showing all the dissociation is called the complete ionic equation. I will never ask you to write the complete ionic equation. The AP will never ask you to write the complete ionic equation. But you might find it useful to get to the net ionic. And let's talk about that. So when we look at this equation, think of it as an algebraic statement. We have 3x over here, 3x over here. We have 3y over here. We have 3y over here. We're starting and ending with 3 nitrate ions and 3 ammonium ions. So what does that say about nitrate and ammonia? They're not doing anything. Well, if they're not doing anything, why do we need to even consider them as part of the reaction? They're really not. They're just sitting there watching, and we call those spectator ions because of that. So when we talk about the net ionic equation, we just eliminate spectator ions. So I just take out the nitrate and the ammonium, and I'm left with 3 silvers plus phosphate yields silver phosphate. There is my net ionic equation. Okay, as I said, you're always expected to write out the net ionic equation. How much of the other 2 versions, the complete molecular, complete ionic, that is up to you entirely. So try these. Calcium chloride plus potassium carbonate, magnesium chloride plus copper 2 sulfate, tin 4 acetate plus lithium chromate. All right, pause this video, give those a try, but I am going to go on. So calcium chloride plus potassium carbonate is going to give me calcium carbonate plus potassium chloride. Now I check my solubility rules. Calcium chloride is soluble, it dissociates. Potassium carbonate is soluble, it dissociates. Calcium carbonate is not soluble, it does not dissociate, but potassium chloride does. So now potassium and chloride are my spectator ions, leaving me with the net ionic. Calcium plus carbonate yields calcium carbonate. Remember, charges have to be written. If you write it without the charges, it's wrong. There is no partial credit. It's just wrong. Magnesium chlorate plus copper 2 sulfate. So we swap around. We're going to get magnesium sulfate and copper 2 chlorate. Magnesium chlorate. Chlorates are always soluble. That dissociates. Sulfates are usually soluble. That dissociates. Magnesium sulfate. That's a sulfate. Usually dissociates. Copper 2, and here we have a chlorate again, that dissociates. So everything dissociated. Here is my complete ionic equation. This thing is going to conduct electricity very well. But that means that there really is no reaction because everything is a spectator. I would cross out everything. There's no reaction. If I mix these 2 solutions, nothing happens. Okay? So when we say no reaction here, we're saying that nothing is going to actually happen. All right, and the last one, tin 4 acetate. You could write acetate C2H3O2 if you like, plus lithium chromate yields tin 4 chromate plus lithium acetate. Acetates are soluble, so we get a tin ion and 4 acetates. Lithium compounds are always soluble, so we get 4 lithiums and 2 chromates. You nearly got me. All right. And then we would get our precipitate of tin 4 chromate, and then lithium acetate would dissociate very well. So now we eliminate spectator ions of lithium and acetate, and we're left with tin 4 ions plus chromate yields tin 4 chromate. All right. Now we're going to go right into section 3, representations of reactions. You may remember from the last unit we talked about representations of solutions. Same idea, but now we're just talking about reactions. So in that unit we talked about the idea that you need to think about things in terms of proportionality. So keep that in mind. That's a huge factor here, because we also have to eventually start talking about balancing of equations and stoichiometry and whatnot. And that's really all about proportions. So as we look at this reaction, I can see that, reasonably guessing that red is usually oxygen and whites are usually hydrogens, that we have 2 waters, and I'm getting 2 hydrogens plus an oxygen. I know my diatomics. Okay, so even if this wasn't quite oxygen hydrogen, at least it makes sense because I'm getting 2 different diatomics out of this. And that is another important thing you need to remember here. You got to keep track of your diatomics. Hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, chlorine, Hofbrinkel, and you got to know it. Again, yeah, that's all. There's the Hofbrinkel, all redundant here. Okay, so again, you might be asked to interpret something about the reaction or to say which one represents it the best. Here's a question that was a number of years ago that I always love this. I use this as a reference all the time. So we're told which of the particular diagrams best represents the synthesis of water at 125 degrees. All right, so we're talking about synthesis of water. We're making water, okay, from its elements. So it's got to be hydrogen and oxygen. Now, a moment ago, we talked about hydrogen and oxygen being diatomic. So I could eliminate A and C right off the top because they're not diatomic. They're not diatomic. These are diatomics, okay? So now it just comes down to the proportionality and understanding the ratios, okay? So if we were to look at the reaction real quick here, and talk about the fact that it would be 2H2 plus O2 yields 2H2O. The ratio of hydrogen to waters should be the same, but the oxygen should be half as much as either of them. Okay, so that's why when we look at this picture, it should be pretty easy to see that the answer has got to be C, because there are 1, 2, 3, 4, 5, 6 of the hydrogens, the little ones, but only 3 of the oxygens, and we're getting 6 waters. That makes sense. Here, we have 6 hydrogens and 6 oxygens and making 6 waters. Well, that's not right because we'd have extra oxygens left over. So, no bueno. All right, so there we are. It wasn't that long, a little bit longer, but now you're good to go for sections 2 and 3. All right, ciao for now.